Now we have a metal rail, metal bar, long metal bar, bent into an elongated U shape with the two branches of the U becoming parallel and separated by 0.6 of a meter. We have a bar in contact, the conducting bar in contact with the conducting U, the rails, and we're moving that bar at 8 meters per second. There's a magnetic field of 0.005 Tesla times K coming out of the board. So the XY plane is the board, and the Z-axis is coming out of the board, and the current is coming out at you. So a magnetic field, 0.005 Tesla times K, because of course the field is coming out of the board in the Z direction. That's the direction of the K vector. The EMF is negative derivative of the magnetic flux. Okay, and we want to calculate that. Now, there is a changing magnetic flux because we have a changing area through which this magnetic field acts. Now, before we go into that calculation, let's think about how you might have originally thought about this question. Let's imagine you have a positive charge somewhere within this conductor. Now, if it's a metal conductor, we know we don't have 3 positive charges. We know it's negative charges, but let's just keep the signs simple by assuming a positive charge. Negative charge is obviously going to go the opposite direction. So the question is, if you have a positive charge here, it's going to experience a force because it's moving through a magnetic field. And then the question is, what's the direction of that force? Okay, so what's the direction of a force on a positive charge moving at 8 meters per second in a magnetic field coming out of the board? Well, that should be pretty obvious. We know that the force is QV cross B. At least I hope that's something we're pretty familiar with by this point, and pretty comfortable with. Let's see if we can raise the camera just a little bit. Q is a positive charge. Didn't ask you how much force, just ask you for the direction of the force. And how much force depends on how much charge. V is in this direction, so here's V. B is coming out of the board. Now, if the board was flat here in the Z-axis in this orientation, then B would be like so, and the force would be in the positive X direction. If X is this way and Y is this way, now this force is in the negative Y direction, sorry. The negative Y direction would be downward if this is the orientation of your X and Y axes. So that positive charges would tend to accumulate toward this end of the bar, negative charges toward this end of the bar. You would in fact have a charge gradient, a linear charge gradient from one end to the other, going from negative to positive. So you'd have a linear gradient of charge density. Okay, charge density would be negative here, positive here, and it would gradually go from negative to positive, being 0 here and then reaching its maximum here. The result of that would be that positive charges would be repelled from this end and attracted toward this end, so that a current would flow in this direction around the loop. Now, let's see what we get if we calculate this in terms of the information that we have. Negative d phi dt. Okay? Now, the magnetic field is 0.005 Tesla, and that isn't changing. The derivative, therefore, is the derivative of the area with respect to time. So, phi equals V times A of t. And we can confirm that the dot product is going to have magnitude B times A of t. So that the derivative of phi, B is a constant, area vector, the area of T is going to be the variable because, of course, as the bar moves, we're getting more and more area. So, okay, we get an EMF of 0.005 Tesla times the derivative of the area. What's the derivative of the area? Well, first of all, the area is not writing a function necessarily for the area, but relative to some point. The area is going to be 0.6 meters times dx dt. Okay, it's the motion, the 8 meter per second motion in this direction is changing the area. So if we multiply that 8 meters per second, which is your dx dt, by the 6 meters, we're going to get the rate at which the area changes. So we have 0.005 Tesla multiplied by 0.6 meters times dx dt. dx dt is 8 meters per second. So this calculation comes out, in this case would be negative 0.024 Tesla meter squared per second, or negative 0.024 volts. Being a little careless with signs today, but trying to be a little more careful when I go back through this. Okay. So we have a negative 0.024 volts, and what's that mean? Well, the positive direction of rotation is this way, the negative direction is this way. It means that the voltage is going to drop in this direction, and that's the direction in which conventional current is going to flow. So, well, that's actually the answer to this question. And this is a very common configuration of a metal bar moving through space. And this idea, this calculation of the force when a charge within the bar tells you how the voltage is going to change across the bar. Or up bar on rails in contact, changing its position. So very common. You're going to encounter this in several of the sign problems. It's a very important idea.